We'll turn it over to our next speaker, who is Ben Douglass, is going to talk to us about impact crater geomorphology as evidence of subsurface water ice on Mars.
Good, that's related to the last talk, except it's not a more.
Microphone, please.
It's on. It's on.
Oh, it is. Okay.
Oh, is it on?
Everything is on. Yeah.
Can everyone hear me?
Yes.
Or I guess, can everyone online hear me?
Yep. You're showing up in the trailer.
Okay, perfect.
Yep.
All right.
And it's almost as if someone who planned the schedule planned those talks
Yes.
that are related to be close together.
I appreciate it. The last talk was focused earlier in Mars's history, but my talk is about more recent impacts in the Amazonian period. In fact, probably in the later Amazonian period. So hello, my name is Ben Douglass. I'm a graduate student at ASU. My advisor is Jim Bell, and my research has pretty much always focused on impact craters. I initially was on the moon, but now I'm looking at impact crater geomorphology and using it as a tool to search for subsurface water ice on Mars. So why do we care about craters and why do we care about water on Mars? So craters present a unique method to detect deep subsurface ice, deeper than other methods which may only look, 1 meter deep. Impact craters can allow us to look at the subsurface hundreds of meter deep through the evidence presented in their morphology. So we also care about water because to support human activity on Mars, we want to have water there as a resource. We also want to find it as close to the equator as we can possibly find it. That would be ideal. Also, in the search for extraterrestrial life, we want to follow the water. So if we understand better where there's water on Mars, that can help us. These craters don't only reveal deeper subsurface ice, they can also go into the geologic past from the time of impact. So a impact, occurs, say, let's just say 500 million years ago. There's some sort of fluidized ejecta potentially, or there's the depth to diameter ratio that can reveal the state of that surface or subsurface from that time of impact. So just an overall outline, I'm going to start with a pilot study of crater depth to diameter ratios that span from pole to pole, and I'm going to evaluate how they vary with latitude. I did that pilot study, then found that I could improve it. So rather than publishing that, I'm making a different study that builds on it and improves, and that is the one that will be, in the end published. I also have future research ideas that I want to introduce having to do with rampart craters with their characteristic fluidized ejecta and concentric crater fill, which I'll go into at the end. So just some background for my pilot study. Craters which form in icy subsurfaces are hypothesized to be relatively shallow, so that being a smaller depth to diameter ratio. And models such as Sempton Stewart 2008 predict that impacts in icy surfaces will result in shallower craters. And that study, they predicted it due to the strength mismatch in rock on top and lower strength ice below. And then, of course, we have what I would say is iconic study by our Stuart Robbins right here, where they looked at craters all over Mars. They made a database. They included depth to diameter ratios of craters down to 3 kilometers. They used MOLA gridded DEMs, which are 463 meters per pixel. So we now have access to higher resolution DTMs. I tried to use a higher resolution DTM, found out that maybe it wasn't the best one. So I'm also trying to look at more localized, higher resolution areas as well.
I have thoughts on that if you'd like to.
Okay, we can talk now or later?
I don't mean now.
Okay. Let's definitely chat. Let's definitely talk. And then I'm also going to be making a comparison to hydrogen maps by studies such as Feldman et al. 2004 and Pathar et al. 2018. They use neutron spectrometry to search for water equivalent hydrogen. So they're searching for hydrogen, and we're calling it water equivalent hydrogen because water has hydrogen in it, but it's not necessarily water. So I'm going to be using this for a comparison later in my study. So my goal is to use crater depth to diameter ratios to estimate the distribution of subsurface ice in Mars's geologic history. My hypothesis, first of all, for the equator is that craters will be relatively deep at the equator. In the polar regions, the craters will be relatively shallow, and then the mid-latitudes will have a transition from deep to shallow, and that's really where the interest lies in where that transition occurs and what that could imply about the historic span of subsurface ice on Mars. So I used JMARS primarily. So I measured crater depth and diameter to get the D/D ratios. For the crater depth, I used the crater counter tool in JMARS, and I took 20 radial cross sections of the crater. We've talked about maybe updating this method, so I'm going to update this, but this is for my pilot study. And I took the average of the 20 maximums there, and I then took the lowest point in the crater and I subtracted it. And then for the diameter, I took 4 measurements across the crater using CTX image for each crater. The DTM that I used is a USGS blended MOLA HRSC global DTM. The reason I initially used this is because it's the highest resolution global DTM that's out there right now. But I'll go into a little bit more, but there's some issues with it. So uh, some constraints that I have for my craters are I'm using craters that are 2 to 8 kilometers in diameter. On the lower end, I'm limiting it to 2 kilometers because the DTM has a resolution of 200 meters per pixel, and I want to have at least 10 points across. So 200 times 10 is 2,000, so 2 kilometers. And the 8-kilometer limit I put because I want to look only at simple craters. And though there are some complex craters that are smaller than 8 kilometers, I can check if there's a central peak. I don't want to use any craters with a central peak because that defeats the purpose of the depth diameter ratio comparison. I define the fresh looking craters that I'm looking at as having a crisp rim, a bowl shape, and ejecta in most cases. And I'll show you the locations of the 3 regions that I'm looking at. So I'm wanting to compare different latitudes. So I chose 3 10-degree wide diameter bins from 10 to 20 degrees, 120 to 130 degrees, and 170 to 180 degrees east. So these, or yeah, 180 to 190 degrees actually. So I chose these regions because they don't have, so many of the volcanic provinces, they don't have the basin, so it's easier to make those comparisons across latitudes. Of course, there will be small changes still, but I'm trying to minimize those. And in each of the regions is about 150 craters. So these are the results for one of the regions. I'm just going to start with one and then we'll open it up to all 3. But we find overall that indeed craters are shallower toward the poles as expected. Specifically, all depth to diameter ratios below 0.05. So in 60 to 90 degrees north and south, all of the depth to diameter ratios are below 0.05 in this region. And then in the equator, 30 degrees to minus 30 degrees north, all the depth to the diameter ratios are above 0.05. And then there seems to be a gradient going between the two, which could indicate, actually a gradient of ice or maybe kind of patchy gradient of ice in the subsurface. There also is an interesting difference in the north and south where the general pattern of that curve seems to be shifted a little bit toward the south. It's centered around 10 degrees further down, so around 10 degrees south. That could have something to do with the hemispherical elevation dichotomy. I have a plan to evaluate that more. And so here are all 3 of the study regions and their results. So the same one that I looked at is on the right here, and then these 2 on the left are new. So they have arrows pointing to each of the 3 regions again. And I'm going to go through some interesting similarities and differences between them. So they overall have the same shape, but there are some intricate differences. This here is the 10 to 20 degree east region. So I also just made a kind of more simplified version on the right where I split the data into 10 degree bins just to help see the patterns, but we can mostly look at the image on the left. So there is an odd lack of especially deep craters toward the equator. And you'll see in the next one, just to show a comparison, there's definitely a lack of especially deep craters with depth to diameter ratios, say, greater than 0.13. And I have a potential explanation for that I'll be showing. Then in the 120 to 130 degree region, the craters are especially deep. If we go back to that first one that we looked at, they're deeper than the other regions. So that's an interesting difference. And there's also these anomalies of these polar craters that actually are surprisingly deep. There's 4 of them. One of them especially is quite deep. That crater in particular actually did look especially fresh with a pretty sharp rim, which is more rare for the polar regions. So that's something I'm going to look further into in my next study as well. And also then here's the same region. This one was more what I was expecting, more of a smoother transition, whereas the previous 2 seem to have a little bit of a sharper transition from the shallow to deep. For example, at around 40 degrees, minus 40 degrees latitude here, that transition is more sharp than it is here. And so again, the anomalies that I was looking at are the 10 to 20 degree east region. There's that equatorial anomaly with the lack of deep craters. There's also this area in the southern part of the 10 to 20 degree east region where the craters are a little bit deeper than we would expect. I did actually find that it roughly aligns with how the south polar layer deposits are offset. So the 10 to 20 degree east region does pass over where the south polar layer deposits are offset away from it. So that could indeed just be a slightly less icy region. And then, of course, there's the especially deep depth to diameter ratios in the 120 to 130 degree east region as well. So I'm going to do a comparison to Feldman et al. 2004. Again, they used neutron spectroscopy to create a water equivalent hydrogen map. Again, this is just hydrogen that they're detecting. They found around 8% hydrogen present in these 2 spots near the equator, which was a bit surprising. More surprising is that the first anomaly I talked about, the lack of deep craters, of especially deep craters toward the equator, happens to line up with the hydrogen that was detected. This isn't something that I'm going to make a conclusion from yet, but it's something that is surprising and I'm going to look further into in my next study. It could be interesting, but not making any statements about that yet. So just in summary, for the pilot study, my conclusions are that craters within 30 degrees of the equator have large depth to diameter ratios, all greater than 0.05, tending to be more like 0.1 to 0.15. Most craters, besides those 4 anomalies, have depth to diameter ratios greater than or less than 0.08 at the poles, at the polar regions. And craters in the mid-latitudes have varying depth to diameter ratio, and the transition tends to occur around 40 degrees north and south. So this could suggest the historical span of subsurface ice over, say, the last half billion, maybe billion years. We need to better define the ages of those craters, maybe with some crater counting on their ejecta blankets, but it's a bit of a difficult task. However, the problem I was going to address with that is that there's concerns with the MOLA HRC blended DTM. So HRC is not global. The DTMs are not global, so they used interpolation in areas that are lacking HRC coverage. So that's a problem. Also, it's relatively low resolution at only 200 meters per pixel. And if we look at local DTMs instead of a global one, we can get much higher resolution. So instead, I'm wanting to use CTX and HRSC DTMs, mostly CTX because it has higher resolution. CTX has resolution of around 20 meters per pixel, and HRSC DTMs have resolution around 50 meters per pixel. Just as an example, these are cross sections of a crater again, the top being the 200 meter per pixel HRSC MOLA blend, and then the bottom being the HRSC stereo DTM, which is 4 times higher resolution, 200 meters per pixel versus 50. So you can clearly see that there's a difference in the data lining up. So I definitely want to use higher resolution local DTMs rather than that global data set. So I have now an ongoing study where I'm doing something similar. I'm measuring crater depth to diameter ratios using high resolution CTX stereo DTMs in regions of scientific interest, which I'll show next, to evaluate the historical distribution of subsurface ice on Mars. My hypothesis is similar to my last hypothesis, that we'll see shallow craters toward the poles, deep craters toward the equator, and then we can evaluate the transition from shallow to deep as you get closer to the equator. I do expect that it'll still be around 40 degrees where that transition happens. So these are my regions of interest that I'm planning to look at. I haven't looked, I've only looked in region A so far, so I'm happy to take feedback on how I could change these regions since a lot of the work hasn't been done yet. But region A is up above and below the north-south elevation dichotomy boundary. For those who don't know about Mars, some of us are Martians and some of us are lunatics. I've been on both sides, so you know, you're all good. Mars has this odd dichotomy where the northern hemisphere has a younger surface that is lower in elevation, and the southern hemisphere has an older, more cratered surface that's higher in elevation. It's not necessarily just north-south. You can see the rough dichotomy boundary here. Over where there's no boundary is a very large volcanic province. I just decided not to deal with that right now, because it's a little bit more ambiguous and there's more factors in there. So section B is the roughly the latitude where that transition occurs, which is 40 degrees roughly. So I'm going to be looking around 5 degrees north and south and seeing how that transition, whether it's consistent at all longitudes or whether it changes, and just further characterize it with that high resolution data this time. I'm going to be trying to look more at the anomalous high depth to diameter ratio craters in the polar regions, the ones that have, say, you know, a 0.15 to 0.1 depth to diameter ratio that you wouldn't expect in the polar regions. And I'm going to also evaluate the equatorial regions where using neutron spectroscopy, 8% hydrogen was detected. I find it very surprising that, you know, my data is matching up with that, and I'm suspicious of it because I just think it would be very odd if there was subsurface ice at the equator. So I'm going to just look further into that with a high resolution and see, is there actually something going on? Is it even related, or is it just a coincidence? It's kind of a screenshot from QGIS where I'm starting my work. I've so far looked at 25 craters selected with pre-existing CTX DTMs. I've also learned how to create CTX stereo DTMs using the AIM stereo pipeline, but to minimize the amount of work, I'm trying to also use as many pre-existing ones as I can. And so I did an example DOVD ratio calculation, but we have talked about updating my method to be more robust. So I'm going to make that change. My goal is to have a paper. My advisor is really pushing me to have a paper at the end of the year. It might be more like spring. We'll see.
Advisors push and then students end up doing when they do it.
Yeah. I was like, I don't think this will be ready for the end of the year. And then, you know, he's like, you should go for it. I'm like, okay, I'll go for it. So these are examples of the so I basically just was trying to kind of do a proof of concept of making my own CTX digital terrain model. And so I created this using the AIM stereo pipeline, which I'm very proud of. It took a lot of work to get there. And so I am going to basically be filling in holes where there weren't ETMs available at the craters that I wanted. Assuming that there's two images, from different angles that I can use for, that stereo DTM. And I'm going to finish region A. I'll look in regions B, C, and D as well. Happy to take feedback on those regions too. And I'm planning to apply for funding for this research through MDAP as well. So I also wanted to talk about some future research ideas I have, since I'm thinking at this point in my PhD about, what are the chapters of my thesis. So I've got some ideas for, what those other chapters might be. So just some background about those future research ideas. So I am wanting to look at fluidized ejecta at rampart craters. The So you can see in the picture that this is kind of odd ejecta where it almost kind of looks like a splatter a little bit. And there's these raised ramparts at the end of the ejecta, at the end of those lobes as well. There's a lot of different names for them, but I kind of switch between fluidized ejecta and rampart craters in general. And so this ejecta is hypothesized to be caused by ground ice at the impact site. So they would form during the impact. So they would tell us about the condition at the time of impact, say 250 million, 500 million years ago, so however old the crater is. The other thing I'm wanting to look at is concentric crater fill. There's essentially these concentric lines that are inside of the crater in this infill, and they're hypothesized to be caused by glacial deposits that are covered by regolith. So as we were talking about in the last conversation a bit, Mars precesses a lot over time, and so that changes, where ice can be stable. So perhaps in these craters, ice was stable there, it got covered by regolith, and that either helped to preserve it, or at least it created this evidence of ice that was once in this region where there's not ice today. This crater's at 29.9 degrees north, which is surprisingly far toward the equator for there to be signs of ice. So perhaps there could be subsurface ice there today, or this could just be evidence that there was once subsurface ice there. So for the rampart craters, my ideas so far are to measure using CTX DTMs the rampart height. So at the end of the lobes here, there's that raised, what's called a rampart. So I'm wanting to measure the rampart height compared to the ejecta out, or the surface outside of the ejecta. The ejecta area, as well as the lobateness, which is basically, if you can imagine having a circle of ejecta, and then, it kind of gets wavier and wavier. That's kind of what it's measuring, how big are those lobes going out versus are they it's just a circle. And I'm wanting to compare these measurements with each other as well as spatially. And I also have an idea of incorporating ejecta mapping because I want to get more into mapping and kind of put that tool in my toolkit as a scientist. I'm happy to receive feedback and discuss, this topic. Similarly, I'm happy to receive feedback and discuss this topic as well, the concentric crater fill. My goal is that I want to evaluate whether concentric crater fill could indicate preserved subsurface ice, or at least ice that was once present, and this preserved morphology shows that it was once present. My ideas are to survey the concentric crater fill in the mid-latitudes where it's mostly present using HiRISE and CTX data, and compare, toward more 60 degrees at the higher latitudes and more 30 degrees at the lower latitudes, and see how that morphology is different. I also have the idea to maybe model subsurface ice stability at specific craters with the concentric crater fill, and see in theory, could there be subsurface ice this close to the equator, or is that unreasonable based on the current conditions in that specific place on Mars where we see this feature? I also am interested in maybe exploring the role of slumping, because there's parts of these lines in the crater that appear to kind of slump inward toward the crater. And so I was just curious if maybe that it could be that, there's subsurface ice that's slumping inward a little bit, but just an idea. Again, feedback, ideas, very welcome, because I'm just developing this. And thank you for listening, and I'll take questions and discussion.
I can't raise my hand for some reason. I don't know why, but I'm doing it analog fashion. So whenever you get around to it, I'd love to ask a question.
Okay.
I say go for it.
Yeah, go for it.
Okay, thanks. Sorry about that. Anyway, uh, the hand has been disabled from the digital version. So anyway, so really nice, Ben. That's a fantastic review and discussion, and you're on the right track for a lot of different aspects of crater ice interactions. I just wanted to point out, I would encourage you to think a little bit differently. The rampart craters and pedestal craters are really distinctly different, and one of the things you could do. So the pedestal craters, as shown by Pete Schultz and his students, et cetera, are really we've been interpreting them as formed in a regional ice layer, and the pedestal essentially armors the surface, and then the stuff that isn't armored around it goes away when the obliquity decreases, and it leaves the pedestal. If that's true, okay, and it's a testable hypothesis, you can look at the depth diameter relationships of the pedestal craters and say, hey, what's up with this? Because if it's according to our interpretation, then it's definitely impacting into ice. And you could compare those to others in your your database, and start with something is about, I would say, 80 to 90% likely to have impacted into snow and ice. So that's one point. The other point is a lot of your latitude dependent variation. So there's a very recent unit called a latitude dependent mantle from about 30 degrees or 40 degrees north-south to the poles. It's maybe of the order of meters to a few, maybe tens of meters thick. And it's been interpreted to have been deposited relatively recently in the last couple of million years. So that's another potential explanation for some of the latitude dependence you're seeing there too. And I can send you a paper on that too. But anyway, please send me an email, and I've got your email here, so I'll send you one too. Love to continue this discussion. Great work. Press on. It's really needed.
Thank you so much for your feedback. I would love to look more into those points and ideas. Who is this, by the way? Because I'm not seeing.
Jim.
Oh, Jim Head. Okay, perfect. Yeah, I would love to discuss more.
No problem. That'd be great.
Livio,
I'll be in
I saw
touch.
your hand is still up too.
Hey there. So I'd urge you to be careful with your pilot study. As you've noted, there's issues with the MOLA and HRC MOLA interpolated data set. It's especially bad at the equator, so need to be careful with interpreting depth diameter relationships with that data set, especially at smaller diameters. And 2017 or 2018 paper, we showed that there's a pretty big disparity for all craters below 10 kilometers in diameter when you compare depth diameter from MOLA with depth diameter from individual HRC DTM. So have a look at that. And I think if you sort of go through your depth diameter points individually and validate them, you'll be able to extract the real pattern that's there, and not a pattern that's due to a limitation in a data set.
Yes, absolutely. Thank you for that feedback. Since I completed that study, I have learned all sorts of things about this data set. And so that's why I'm not publishing this data set. I'm instead letting it guide my next study. So
Smart move.
wanting to use those high resolution.
I mean, there might be something there, and it's of course easier to work with the interpolated data. I would just say have a look at my paper, because it tells you sort of like how to sort of go about working with that data set and validating the measurements you make.
Okay, absolutely. I will. Thank you.
So we're at the break time, but there are at least 3 questions in the room. So, and online. And okay. So I suggest folks who want to can go to break. The break is 20 minutes long. We will reconvene at 35 past, whatever hour it is in your time zone. All right, continuing with questions.
I may have missed this. If you're looking for that like really high resolution, have you considered using the high-rise DTMs or any products from high-rise to look at these craters? Because it has that really fine like 0.3 meter per pixel resolution.
So from my experience, just looking, just browsing at the high-rise DTMs, I found that they tend to be kind of smaller. Is that true? They're
Yeah.
much smaller. So
So maybe on the lower end, I was thinking.
yeah, so perhaps on the lower end, but my concern was just that they were too small to really be useful for these, 2 to 8 kilometer craters. Also, since I'm making my own digital terrain models and I'm at ASU, I did a workshop at the University of Arizona, which is, a 2-hour drive away. So in theory, I could go to the University of Arizona and make my own high-rise DTMs using socket set, but oh wait, yeah, okay. But Highwish doesn't create the DTMs.
It won't create it, but if the pair doesn't exist, it can put it into the high-rise team to target.
Mhm.
And if they can put it into their observations, then they can target it and get that stereo pair.
Okay, yeah, so then perhaps I could consider using high-rise. Yeah, but my main concern with that is just that the DTMs are so small.
Yeah, and I'm not sure what the upper limit on the size of them are, like off the top of my head, but maybe for some of the smaller craters
Yeah.
you're looking at, it could be a good tool.
Okay, yeah, thank you. Yeah.
Well, I can go, but.
I saw your hand first, and then we can go back there.
Okay. So I have a question that might turn into follow-up research or not, I'm not sure. So the way you're doing your method, you're taking these sort of, pole-to-pole strips and looking at every crater in there. But as you do that, you must be counting craters of very different ages. And you must be looking at the craters are going across incredibly different terrains from the north to the south and the rest. And yet that doesn't seem to matter in your data set as far as I can tell. Should I be surprised at that?
I did particularly try to avoid, pole-to-pole strips that would go through, things like volcanic provinces that would more heavily impact that. There is a decent amount of variation between all 3 regions and, between like even in them themselves, it's not a clean line. There's significant variation. So it is a bit surprising, but I guess
maybe I'm getting at this. On the moon, what we see is that, fresh craters seem to have a much more bowl shape, and over time, there's degradation that happens, we think, from seismic shaking, the rest that causes them to sort of, fill in. That stuff Caleb Fassett has done. So I might expect the same thing on Mars. So if you could convince yourself you have older craters, it might be interesting to see if their depth of diameter is different in a same region than other craters.
oh,
So then, going across terrains, I mean, the south is, of course, a very battered highlands region, while the north is much younger and a different terrain type. And I just was curious, like, how that changes there. So there's some nuance, I think, in everything you're doing, and it might have been some interesting follow-up with it, rather than just saying, okay, well, everything is latitude, and latitude is destiny. Maybe there's more things you could add into that too.
yeah, just bring in more factors.
Yeah, and see if it doesn't matter. If it doesn't matter, that's interesting too.
Mhm. Yeah, so okay, yeah, that's a good point.
Hi, so Michelle Kirkhoff was here yesterday. She's not here, or they're not here today, but hopefully we'll be back tomorrow. Did an extensive study with Bob Grimm in 2017, mapping the spatial distribution of layer detector craters. So I would definitely recommend checking that out and see how it correlates with your study. I'm looking at it and just trying to recall, there's not a significant difference in distribution latitudinally for the layer detector craters. So your question about the presence of subsurface ice and the formation of those was brought up in that study as well. And so there's speculation that must either subsurface ice or a surface ice layer must have been there to form these features. But I would definitely touch base with Michelle just to see what they've worked on and see how it could help inform your future studies.
Okay, yeah, I'll take another look at that paper and look into that. Thank you.
Okay, lots of comments,
Okay,
as you might expect.
we should talk more.
Right, I'll just note that actually, I think Michelle's paper was specifically, they selected certain things and then did it. My paper shows that there is a significant latitudinal asymmetry with layer detector craters locations. Also, Nadine database showed the same thing.
Okay.
There are many more in the high northern latitude, or sorry, mid northern latitudes. Now that said, if you're talking about layered injected in general versus single
Yeah, that was what
double,
you meant, my follow.
or multi,
Yeah, exactly.
then you have different distributions. All right, second point, looking at my thesis paper from a few centuries ago, I agree with what you wrote, or what you showed. I'm fighting to say found the same thing in terms of that almost bowl shape, with very few deep craters right around that spot corresponding with the GRS data.
Mhm.
I didn't do any correlations with that. I just looked at that randomness as clumpy. But that is interesting to see that it's also in my data. Makes me happy.
That's the one that's near the equator, right?
Yes.
Yeah. Mhm.
Yep.
It's surprising.
Yes. That said, I'm not finding an offset, or I didn't find an offset asymmetry as you did. So should look at that a little bit more closely, perhaps.
Mhm.
That said, again, also I agree definitely that blended mosaic has issues. And I was looking back at my email, and yes, you're the person that we were going back and forth with Trent on. Don't use this
Yeah.
for anything. And my word was in 2013, before Livio did his study, I did the same thing looking at MOLA versus HRSC DTMs, and found that you get that artifacting at MOLA smaller than about 10 kilometers, so about 20 pixels. And that's something that I was mentioning earlier today. Someone else is the issue that when you get smaller than about 25 to 30 pixels in a stereo-based DTM, you get shallowing in any craters.
Okay.
So if you're looking at anything smaller than about 25 to 30 pixels stereo, don't trust it.
Okay, so go a bit larger, perhaps.
Yes.
Yeah.
That said, I found the limit for laser data to be closer to about 10 to 15 pixels or so. So laser data is always better, but MOLA at this point is 25 plus years, and so it was good for its time. It would be great if we can go back there with a better laser altimeter. MOLA on the moon is great. So those are my broad comments. Basically, I agree with you in most cases, and lots of caveats, and we should talk more.
Okay, yeah, absolutely. Any other questions or comments?
All right. 10 minutes
Thank you
left.
for staying a bit late. Sorry.